Okay, so we go to magnetic field. Alright. Now in your A2 chapters, you actually only learn three different kinds of field. The first one is gravitational. The second is your electric. Now the last field you will learn in A2 is actually magnetic. Okay. You will notice that gravitational and electric, the equation, the definitions have similarities to each other. Magnetic field has not as much. Magnetic field is quite different in itself. It doesn't bear much similarity to gravitational and electric. Okay, right. So now, what is a magnetic field in the first place? Magnetic field is just simply a region where a force or magnetic force is experienced by a magnet, a current carrying conductor, or a moving charge. In your other two fields, you learn to define gravitational field as simply a region where a force is experienced by a mass. In electric field, you will say that an electric field is a region where a force is experienced by a charge. So in magnetic field, you define it as a region where a force is experienced by a magnet, a current carrying conductor, and a moving charge. Okay, right? So the part where you say that magnetic field is a region where a force is experienced by a magnet. I think this one is easily understood. Why? Because it's magnet, so magnet will interact with a magnet, giving you a force. But why do you say that it is a region where magnetic force is experienced by a conductor, current carrying conductor, or moving charge? Now, this is because there's one fact you need to know. Moving charges produce their own magnetic field. Okay, so whenever you have a charge and it moves, the charge will actually produce its own magnetic field. So here, if your moving charge has its own magnetic field and you put it inside another magnetic field, obviously you're gonna have magnetic force. When your moving charge is producing its own magnetic field, it is acting like its own magnet. Okay, it's akin to a magnet in itself. So if you put it inside a different magnetic field, the charge will experience a magnetic force. Okay, so that's the reason why we say that if you have a current carrying conductor, that's the reason why we say that a moving charge, if you place it inside a magnetic field, it will experience a magnetic force. Likewise, we will also say that a current carrying conductor will experience a magnetic force inside a magnetic field, simply because current carrying conductor is carrying current. Current is actually flow of moving charges. So it therefore will have its own magnetic field. It therefore acts something like a magnet, such that if you place it inside another magnetic field, it will experience a magnetic force. So in terms of your definition for magnetic field, you can write either this one, the region where magnetic force is experienced by a magnet, or region where magnetic force is experienced by a current carrying conductor, or by a moving charge. You don't necessarily need to write all three. Just one of them will do. But if you want to be safe, just write all three. Okay, right? Now, when you want to represent magnetic field visually, you will use field lines to represent magnetic field. So whatever you have learned in your electric and gravitational field about field lines, the general characteristic would also apply here. So simply put, we will just say that if you're talking about spacing of field lines, if you're talking about the field lines, what we will tell you is that the spacing of field lines represent field strength. Okay, the closer the lines, the stronger the field. Okay, then after that we will tell you that the field lines always make perpendicular contact, always make perpendicular contact with the surface. Okay, right, there's another one. Then after that we will then tell you also about the direction of the magnetic field line. Your direction of magnetic field lines is determined by direction of force acting on an isolated end pole placed at that point. Okay, the direction of a magnetic field is determined by direction of force acting on an isolated end pole placed at that point. Okay, so in general, this is what you need to know about your magnetic field. Spacing of field lines as before represents your field strength. The closer the lines, the stronger the field. And then secondly, when your field lines is making contact with any surface, it must be making perpendicular contact. And then your field lines also have a direction. The direction is always in such a way that its direction will always follow direction of force acting on a isolated end pole placed at that point. Okay, so that part is okay. Right, so other things about magnets is that you just need to know that the magnet usually has an end pole and south pole, just like a charge has positive and negative. And then after that, what we'll tell you is that if you have unlike poles, the magnets will attract. South pole will attract north pole and vice versa. But if you have like poles, meaning you say north and north, south and south, the magnets will repel. Okay, so this is in general certain things that you by right should know lah. Okay, now if you were talking about magnetic field lines around a bar magnet, this is how your magnetic field looks like. You've probably learned about this in your IGCSE or SPM already. So direction of magnetic field line is determined by direction of force acting on an isolated end pole. Just know that in general, the field lines normally point out from your end and they will go into the S. Much in the same way when you're talking about positive charges, you notice that in general, the field lines always go out from positive, but the field lines always go in for negative, right? You can think of something similar for magnetic field also. If you see N pole, by right, the field lines will be pointing outwards. If you see S pole, the field lines will be pointing inwards. It's mainly because if I put an isolated N pole here, the magnetic force will be this direction. So the direction of the field lines will be outwards. Likewise, for this side, if I put an isolated N pole, this and this will attract. So my magnetic force is this side. My field lines will follow the force acting on the isolated N pole, therefore going inside. Okay, so that is in general what you need to know. Okay, now as part of your syllabus, you are required to know how to draw the magnetic field lines around a few cases. The magnetic field lines around a bar magnet, this one everyone knows how it looks like. The ones they will require you to draw to know is the magnetic field lines around a current carrying conductor, around a solenoid, as well as a flat circular core. Now, if you're talking about the magnetic field lines around a current carrying conductor, this one is very easy. By right, when you have current going through a conductor, as I mentioned, you have flow of charges, you have moving charges, you will produce magnetic field. How do you know how is the pattern of the magnetic field? It will usually be a pattern of concentric circles. Okay, so it will be a pattern of concentric circles. You will be required to know certain things about that pattern of concentric circles. The first thing you need to know is how to determine the direction of the magnetic field lines of the represented by the concentric circles. If you want to determine the direction of the magnetic field lines around the magnetic field lines, you need to use your right hand grid rule. There's a certain way in which you can determine the direction of the magnetic field. You use what you call a right hand grid rule, where we tell you that the curl of your finger represents the direction of the magnetic field, while the thumb represents the direction of the current. So if say you wanted to draw the magnetic field around a current carrying conductor, you would just need to use your right hand to do so. So if say I tell you that your current is going upwards here for this wire, if you use your right hand grip rule, you will notice that if you align your thumb upwards, the curl of your finger is going in this direction. So this tells you that the magnetic field is going anti-clockwise here. Alright. Likewise, if your current is going downwards, you align your right hand grip rule where your thumb points downward, you will notice that the curl of your finger is going in this direction. It is going clockwise. Okay. So you want to determine direction of your magnetic field, use your right hand grip rule. Okay. Now you won't be asked to draw your nowadays you won't really be asked to draw your magnetic field lines in a 3D pattern like this. A lot of times nowadays they will ask you to draw it in a 2D pattern like this, where you're basically just looking at it from the top. Okay, so you're trying to draw the magnetic field lines in 2D, where you're just looking strictly from the top or bottom if necessary. Usually it's from the top. Okay, how will you draw it? You will draw those pattern of concentric circles where the direction is determined using a right hand grip rule. There's another thing here that you also need to know. If say you're looking from the top, like this one, how would you draw the current here? Okay. Now we will tell you that if you want to represent the current when you're viewing it from the top, it'll be like this. You will draw a circle and then there's a dot here. Okay. If you're talking about this side and you're looking from the top, the current will be represented as a circle but with an X or with a cross. Okay, this dot here, you can think of it as you looking at the tip of an arrow. You can think of your current as something like an arrow. If you're looking at it from the top, you're actually looking at the tip, so you're looking at the dot. Okay, likewise, if your current is going downwards, it's like the arrow is going downwards like this. Okay, and you're looking at it like this. So what you're seeing is the tail of the arrow, so the cross is like this. Okay, so in general, if you want to represent a current going in and out of your plane of viewing, if it's coming towards you or coming out of the plane of the paper, it is a dot. If it's going away from you or going into the plane of the paper, it will be represented by a cross. Okay, so that part is okay. Now, you know how to draw the direction, you know how to draw the current. When you draw your pattern of concentric circles, you need to be careful about the line spacing of your circles. Okay, you see the spacing between the lines here are not the same. Remember I told you just now that the spacing of your field lines represent the field strength. Okay, so in general, when you have a magnetic field that is being formed around a wire, if you go further away from the current, if you go further away from it, if your R increases, your field strength will drop. Okay, field strength is sometimes known as flux density. Okay, when you go and do your questions, we normally don't call it field strength in magnetic field. In your gravitational field and electric field, if you want to know how strong a field is, we normally call it field strength, right? But in your magnetic field, they seldom use the term field strength. They instead call it flux density. Okay, right? So you just know that when they mention flux density is actually referring to field strength. Okay, and the symbol for field strength or flux density is B, symbol B. In gravitational field, your field strength is represented by symbol G. In electric field, your field strength is represented by symbol E. Alright. In magnetic field, your field strength or flux density is represented by symbol B. Okay. So here, back to what I was saying, if you're talking about the magnetic field around a wire, the further you go away from the current, the weaker your field. The magnetic field strength will usually be stronger near the current and weaker away from the current. So if you want to draw your pattern of concentric circles, you would then need to draw your concentric circles with increasing distance. Okay, so here if I go further away, my field strength is decreasing. What you know is that the spacing of the lines increases. Okay, the spacing between the lines will increase. Alright, this one I'll just write it as this. Spacing between the lines will increase. Actually, no need lah. You can just write as this. The spacing of the lines will increase. Okay, because the further away you go, the weaker your field. So the weaker your field, the bigger your spacing. Alright, so when you draw a pattern of concentric circles, just be careful. Don't draw it with equalized spacing. Draw it with increasing separation. Okay, right? So that part is okay, right? Now, for the magnetic field that is produced by a current carrying conductor or by a current carrying wire, as I mentioned to you, B is actually your field strength. Okay, it's actually your field strength. Okay. Now, what are the factors that affect the field strength of your magnetic field? You could say that V is actually proportional to I. The bigger the current flowing through your wire, the bigger your field strength. And then it's also affected by your distance. Okay, so just now I told you the further away you go, just now I wrote symbol R, right? I think maybe you don't write it as R, you write it as distance D. Okay, the further away you go, the weaker your field, right? So your relation between distance from the current and the field strength is actually an inverse relation. The bigger your D, the smaller your B. So you combine these two together, you get this. Your magnetic flux density or your magnetic field strength is actually proportional to I over D. You want to get rid of the proportionality symbol, you introduce a constant. It will be B, K, I over D. Now this constant here is actually this one, mu naught over 2 pi. Alright, so the magnetic field strength or the magnetic flux density around a wire is given by this. Okay, now you do not need to remember this equation. Okay, this equation you do not need to remember. If the question in the exam requires you to make use of this, the equation will be given by the question itself. Alright, so this one is not required to be memorized. Okay, notice that it's not inside the yellow box. If it's in the yellow box, that means it needs to be memorized. Here it's not inside. You don't really need to memorize this, but it's useful to know later on for EM induction, the next chapter. Okay, so flux density is proportional to current, is inversely proportional to distance from your wire, distance from your current, so you eventually will get this. Alright, mu naught is just another constant where we tell you it's actually permeability, or it's actually called permeability. It is actually a measure of a medium's ability to transmit a magnetic field. In other words, how easy it is for magnetic field to pass through a medium. Okay, mu naught is actually the permeability of vacuum. Now the value of mu naught itself you can actually get from your data sheet under the second page. It's actually written here. Permeability of free space mu naught is 4 pi times 10 power minus 7 h per meter. Okay, right? Permeability, they will never ask you the definition of it. They will never ask you what it means. Okay, so don't really need to bother so much about this. Just know that it's a constant. Okay, if anything, if you want to know further what it is, it's just something to measure how easy it is for magnetic field to pass through a point. Okay, so that part is okay. So this is just another way of drawing a magnetic field lines. It's actually a repetition of whatever you have here. So no issues. So as I mentioned, the separation from the center will increase. When separation increases, separation of the lines increases, it tells you the field is becoming weaker. So this part is stronger field, this part is weaker field. Okay, all right, so this one no issue. Now, apart from drawing the magnetic field of a wire, you also need to draw the magnetic field around something called a solenoid. A solenoid is just simply a coil of wires with many turns. Think of it as something like a spring. Okay, it will look like a spring. A solenoid looks in a way similar to a spring. It's a coil with many turns. So if you run current through a coil of wire or a solenoid, we will tell you it will also produce a magnetic field. So how does the pattern of the magnetic field look like? It will look like this. Okay. The pattern of the magnetic field around a solenoid or coil of wire actually looks like the pattern of the magnetic field around a bar magnet. Okay, it looks like the pattern of the magnetic field around a bar magnet. Okay, now if you want to draw the pattern of the magnetic field around a solenoid, we won't ask you to draw it in 3D like this. We will just ask you to draw it in 2D also. So how we draw in 2D is that we assume that you cut the solenoid in half. Where you cut the solenoid in half, across in half, that's where you start to draw. So this one is a view of that solenoid cut in half and you drawing the magnetic field around the plane in which you cut the solenoid. Okay, so here, if you want to determine the direction of your magnetic field, you again will need to use your right hand grip rule. How you use the right hand grip rule here will be a bit different. What we will tell you now is that the curl of your finger will represent current, the thumb would represent field direction. Okay, it's different from the previous case. Just now when you use your right hand grip rule for wire, the thumb was the current, the curl of your finger gives you the direction of the field. In the case of a solenoid, the quantities are reversed. This time thumb is no longer current, but it is field direction. This time the curl of your finger is no longer magnetic field direction, but rather the current. Okay, so you will still use your right hand grip rule to determine the direction of your to determine the direction of the magnetic field around a solenoid. Okay, just that you just switch the quantities for the finger and the curl of your finger. So now if your current is going like this, you try to visualize it as your current as going like this. I mean, for the diagram that's given to you here, you can actually visualize your current as going like this. Okay, your current is going like this, right? It is actually going like this. If you use your right hand and try to align your curl of your finger such that it follows this current direction, your thumb should be pointing like this. I mean, your right hand should be pointing like this right now. Okay. The curl of your finger should be following the current direction. The thumb should be pointing here. This one indicates to you the direction of the magnetic field. So your arrow should be pointing towards the right. Okay. So where the arrows come out from, this one is your north pole. Where the arrows go in, this one is your south pole. Okay. So this is how you determine the direction of your magnetic field. Okay. Now, inside the solenoid itself, when you want to draw, make sure that the field lines are equal spacing. Why? Because field is uniform inside solenoid. Inside the solenoid. Okay. So you want to determine direction, use right hand grip rule. You draw the arrows, and then when you want to draw the lines, please just make sure that the lines inside the solenoid itself have equal line spacing, because the field is actually uniform inside the solenoid itself. Okay. And then another thing here also will be this part here that you see. Now, the part that you see here over this side, this one here is representing the current. Okay. Now, if I mentioned to you just now, this diagram is obtained by you cutting the solenoid in half and you drawing what you see at the plane at which you're cutting, right? So at this point here, you see this is where current is coming out. Okay, so it will be represented by a dot. This part here at the bottom is where current is going in at the plane where you're cutting. Where you're cutting right now, this part here is where you see current is coming out. This part here is where you see current going in. So for the part where current is coming out or out of the plane of your paper, you will represent it by dots. And then this part here where the current is going into the plane of paper, you will represent it by cross. Okay, so this is just one thing to understand. Now, for the magnetic field strength or magnetic flux density around a solenoid, there's another equation that you can use, which is this one. Now, for a solenoid, you know that the field strength should properly increase with increasing number of turns. And then likewise, the field strength should also increase with more current. So if you combine both of them together, it becomes B proportional to Ni. So you want to get rid of the proportionality sign, you introduce a constant, it will become this, where your constant is actually mu naught, the permeability of free space that you learned before. And again, this equation is not required to be memorized, so you don't really need to know this. You don't really need to memorize this. It's just that it will be useful when you go to EM induction chapter later on. Okay, right? So this is the pattern of the magnetic field around a solenoid. The last pattern of magnetic field that you need to learn is that around a flat circular core. Now, the pattern of the magnetic field around a flat circular core is actually similar to that of a solenoid. The only difference here is that, you see, your core is actually just one turn. Your flat circular core is actually just one turn of your solenoid. Okay. If you're talking about solenoid, it has many turns. It has many cores combined together. If you're talking about a single flat circular core, it's actually just one turn on your solenoid. Okay, the pattern of the magnetic field that you get is similar to solenoid. Just that if you want to draw, everything here is shortened out. Okay, the pattern of the magnetic field around a flat circular core will be similar to that of solenoid. It's just that you're shortening out all the other things. Okay, this pattern that you see here is actually similar to this, just that for one core, everything else is shortened. You see, you get this pattern here. Okay, if you want to find out what is the pattern, what is the direction of your magnetic field you can also again use your right hand grip rule. Okay, where here we will tell you the thumb represents the direction of the magnetic field, the curl of your finger represents current. If you see here, the current is actually flowing like this. If you align your right hand such that the curl of your finger follows the direction of the current, you will notice that your thumb points outwards. So the direction of your magnetic field is outwards. Arrows coming out is north pole. Arrows going in is south pole. Okay, now, okay, remember I just now told you that when you have a current that is flowing through a wire, if you place it inside a magnetic field, it will experience some magnetic force. So say right now we have a wire where you have a current flowing through it. You place it inside a magnetic field. You're interested in knowing the amount of force acting on that wire. You're interested in knowing the direction of the magnetic force acting on the wire. So how do we go about in testing that? If you want to know the magnitude and direction of the magnetic force acting on the wire. So one way we can do that is actually by doing a experimental arrangement similar to this. So what we do is that you have a current carrying conductor, which is this one. We clamp it in between two retort stands. The retort stand is actually not shown here. We clamp it in between two retort stands, and we make sure that the wire is actually in between two bar magnets. The bar magnet is actually the ones shown here and here. Okay, so we are interested in knowing the direction of the magnetic force. We're also interested in finding out the magnitude of the magnetic force. So like here right now, based on the arrangement of the apparatus, what will happen is that this wire is now connected to a battery supply, and there's a switch here. Once we close the switch, current will actually start to flow from the battery through the wire and then back to the battery itself. So when current is flowing through this wire here, it will produce its own magnetic field, and then it interacts with the magnetic field of the existing magnets. So you have a magnetic force acting on the wire. So if you want to predict the direction of the magnetic force acting on the wire, you need to make use of Fleming's left-hand rule. Okay, I won't really talk so much about this part because this one tells you how to predict the direction of the magnetic force by looking at the interaction of the field lines. But this way of looking at magnetic force is actually not really tested in your syllabus. So I won't talk so much about this. I'll just skip this one. I'll just go straight to telling you how to predict the direction of the magnetic force acting on a wire. Now, if you want to predict the direction of the magnetic force acting on a wire, you need to use Fleming's left-hand rule. Okay, the ones before this you were using the right hand grip rule. That one was telling you the relation between current and magnetic field direction. For Fleming's left hand rule, this one tells you specifically about the direction of the magnetic force acting on a wire. Now Fleming's left hand rule looks like this. Okay, you have to make your left hand, you have to use the first three fingers of your left hand, and then you need to orientate them such that they're at 90 degrees to each other. Where now we will tell you that your thumb represents magnetic force, your index finger represents the magnetic field, and your middle finger represents current. Okay, so FBI. Okay, so now for example, like in this case here, where I have the wire and current is flowing through it, and it's the wire with current is inside a magnetic field. I have magnetic force. I'm interested in knowing what's the direction of the magnetic force. You can think of an example like this. All right, say this is a small cutout of just now that diagram there, and this is another view of it. This is my wire, and I know that my current is going in this direction. This is my I. Okay, Now, if say for example, the magnet was N here and S here, the direction of the magnetic field is actually going to be from here to here. This is the direction of my B. Okay, direction of B is always from N to S. So if your magnet is N and S here, the direction of magnetic field is going to be in this direction. So your B is here. Okay, so what you then do is that you use your left hand, you orientate your three fingers where your index finger is in the direction of B, middle finger is in the direction of I. Your thumb will thus represent the magnetic force acting on the wire. Okay, now FB here stands for magnetic force. Okay, just like FG stands for gravitational force and FE stands for electric force. So whenever you see me writing FB, it is actually referring to magnetic force. Okay, so your Fleming's left hand rule is used to determine the direction of the magnetic force. But you need to know what is the direction of your B and I in the first place to be able to determine the direction of your FB, of your magnetic force. Okay, Fleming's left hand rule only tells you the direction of the magnetic force, but it will not tell you the magnitude of the magnetic force. So how would you go and determine the magnitude of the magnetic force? You will have to use a top band balance. Okay, so as mentioned to you just now, current running through the wire is in between a magnetic field. This in turn causes the wire to experience a magnetic force. So say for example, in the previous example that I showed you, I told you that this one was N, this one was S, and my current was going this way, and then my B was here. My magnetic force was going on the wire was going to be upwards, right? Okay, so if my magnetic force on the wire is acting outwards, does this mean that my top band balance here, the reading, will it increase or decrease? You see, your top band balance here is measuring whatever is pushing down on it. Okay, you know that if you want to measure anything, you place something on the top band balance, the top band balance will measure whatever is pushing down on it, right? So here, what you have was that the direction of the magnetic force acting on the wire was upwards. So does this cause the reading on my top band balance to increase or decrease? Now, in general, you can just think of it this way. Yeah, I mean, you know in your chemistry lab before, if you're using a top band balance, if your reading increases, that means force is pushing down on the balance. If your reading decreases, that means force is pushing up on the balance, isn't it? In general, if you have something pushing down on the balance, the reading will increase. If you have something pushing up on the balance, the reading will decrease. Okay, so here in your current case, do you expect to see the top band balance reading to increase or decrease? Okay, now here the correct answer would actually be this. Your top band balance reading would actually increase. Okay, the top band balance will actually increase. It will not decrease. Why? Because you see, your wire in itself is actually not resting on the top band balance. You see, as I mentioned to you just now, your top band balance, sorry, your wire is actually being clamped between two retort stands and is suspended in air between two magnets. If anything, it is the magnets connected to this U-shaped bar here that is resting on the top band balance. Okay, the magnetic force that you just determined was the magnetic force acting on the wire. Okay, and that wire was not connected in any way physically to your top band balance. All right, so how are you going to get some reading change here? You have to realize that there are actually two different objects right now in this current system. You have the wire and you also have the magnets. Okay, there's actually two different objects here, the wire and the magnet. So the thing here would be that if your wire is experiencing a magnetic force outwards, your magnet will be experiencing an equal opposite force because of Newton's third law. If you remember Newton's third law always tells you that when you have two objects interacting, they exert equal opposite forces on each other. So your wire was actually interacting with the magnet. That in turn caused the wire to have a magnetic force. So according to Newton's third law, you will also have an equal opposite force acting on the magnet now. If the force acting on the wire was outwards, the force acting on the magnets will be downwards. You will have a FB on magnet here. Okay, so it's opposite in direction to the FB on the wire. This is a consequence of Newton's third law. Okay, so you have a force pushing down on the magnet. The magnet is directly connected to your top band balance, so your reading will increase. That's why you cannot say that your reading will decrease, because the force acting on the top band balance in the first place is actually pushing down on the balance. Okay, so because right now there's a force actually pushing down the balance, so your reading will actually increase. Okay, so far so good with that. Then let me just see whether there's an example you can do. Yeah, there's an example that you can do. This one is under page 11. Okay, so just have a look at page 11 of your worksheet. This is November 16 P42 under the magnetic field chapter. It's a different worksheet now for magnetic field. Okay, so this one is November 16 P42. Okay, just go to that. Question 9. Okay, so now what they have here is something like this. It is a wire that is placed in between a U-shaped magnet. They tell you a stiff wire is held horizontally between the poles of a magnet. It's illustrated in figure 9.1. When a constant current of 6 ampere is passed through the wire, there's an additional downward force on the magnet of 0.08 Newton. On figure 9.1, draw an arrow on the wire to show the direction of the current in the wire. Explain your working. So how do you know what's the direction of the current acting in the wire now? What they mentioned here was that there was a downward force acting on the magnet of 0.08 Newton. Okay, so here you see that FB on the magnet was downwards. Okay, they want you to predict the direction of the current in the wire. Now, what is the direction of current in the wire? You can actually use Fleming's left-hand rule to predict the direction of the wire, the direction of the current. Where just now I told you the thumb represents your magnetic field, your index finger represents B, and your middle finger represents current, right? Correct? So based on what you have here, you want to predict the direction of the current in the wire. You want to predict I, okay? But you need to know two other things. What is the magnetic field it is in? What is the magnetic force acting on the wire? Okay, all this relates to the wire. Okay, all this relates to the magnetic force, and the current relates to the wire. Okay, this one here is the force on wire. This one is the current in wire. This one is the field the wire is in. Okay, so this FB acting downwards, force on the magnet is 0.08 Newton. It's talking about the force on the magnet, not on the wire. But you know, by Newton's third law, the force on the wire ought to be upwards. This would be the force on the wire. So you know FP already. Now what is the field that the wire is in? The field that the wire is in is caused by these two, this N and this S. So I told you that the direction of your magnetic field is from your N pole to your S pole. So it will be from here to here. This is the direction of your B. So if you orientate your fingers to match the FB and B, you will notice that your eye is going from here to here. Okay, so when they ask you to draw the direction, an arrow to indicate the direction of the current, is actually going to be this side. Okay, it will be like this. Okay, so they ask you to explain, you explain it in this manner. They will say that since force acting on the magnet is downward, according to Newton's third law, there will be equal opposite force that is acting upwards on the wire. So then, further to that, according to Fleming's left-hand rule, the direction of the current is from left to right, as shown in your diagram. Okay. Now the magnetic force acting on the wire is equal opposite to the magnetic force acting on the magnet itself. The value is 0.08 Newton. Okay. If you know that the magnetic force acting on the magnet was 0.08 Newton, the magnetic force acting on the wire will also be 0.08 Newton. Okay. Right. How do you know in the first place the magnetic force acting on the magnet was 0.08 Newton? That one is only possible if you have placed this thing onto a top band balance like this one. So when the force on the magnet is pushing downwards on the magnet, your top band balance will measure what was the force pushing down. So if it tells you that this is 0.08 Newton, that would mean that there is the force of 0.08 Newton acting on the magnet. So in return, it's also a force of 0.08 Newton acting on the wire. Okay, so your top band balance will actually give you a measurement of a direct measurement of your magnetic force. Okay, so that one is done. Part B relates something to sinusoidal current. It relates to AC current. This one I won't really talk so much about it first. I just tackle the parts that are related strictly to magnetic field first. Okay, so this one should be okay, right? Then I will go on to another part. The other part should be page 23, but I don't think you can do that one yet. Let me just have a look. Page 23, no, you cannot do that yet. Okay, right. Say for just now I told you that if you want to measure the direction of your, if you want to predict the direction of your magnetic field, not direction of magnetic field, let me just reiterate that. If you want to predict the direction of your magnetic force, you have to use Fleming's left-hand rule. Okay. If you want to measure the magnitude of your magnetic force, you have to use a top band balance. Okay. Now, is there another way in which you can calculate out the force acting on a wire? Is there any way you can calculate out the magnetic force acting on a wire? You can. That one is by using this equation. FP is equals to BI out. If you have a wire of a length L, place if you have a wire of length L that carries a steady current of I and is inside a magnetic field B, and the wire is right angles to it, the magnetic force acting on the wire will be given by this equation. FB is equals to BIL. Okay. Now, it is from this equation tells you the magnetic force acting on a wire. Now, it's also from this equation that you define your magnetic flux density or your magnetic field strength. Just now I mentioned to you that your B is akin to your magnetic field strength, but normally we don't write it as field strength, we call it flux density, right? Now, if you want to define magnetic flux density is defined from this equation. If you rearrange this and make B the subject, it's actually F over IL. Magnetic flux density is actually force acting per unit current in a wire of unit length that is perpendicular to the field. Okay, this is your magnetic field equivalent of field strength. If you're talking about gravitational field, your field strength was force acting per unit mass. If you're talking about electric field strength is force acting per unit positive charge. For magnetic field strength, it is defined as force per unit current in a wire of unit length that is placed perpendicular to the field. So it is very different from how you define gravitational field strength as well as electric field strength. Okay, so just be mindful of that. Okay, it's defined from this equation. Now, magnetic field strength or magnetic flux density is measured in Tesla. There's a special unit for it called Tesla. Okay, if you ask to define a unit of 1 Tesla, it is just simply the magnetic flux density normal to a long straight wire carrying a current of 1 amp that produces a force per unit length of 1 Newton meter. How you look at it is by this. If you are asked to define 1 Tesla, this one is unit of 1. So this one must have a value of 1. So the rest of it must have a value of 1 also. So whatever you define must be in terms of 1, 1, 1, 1, 1. So that's why you get this. It is flux density normal to a long straight wire carrying a current of 1 ampere that produces a force per unit length of 1 Newton per meter. Okay, right. This equation to calculate magnetic force is only applicable for wires. Okay, so this one here, the thing here I need to mention is that this one is only applicable for wires. Okay, it's only applicable for wires at right angle to the field. Okay, it's applicable to wires and it must be perpendicular to the field. All right, what if you have a wire but it is not perpendicular to the field? Say for example like this. This is your magnetic field and then your wire is not placed perpendicular but rather at a certain angle. How do you go and find out the magnetic force acting on the wire then? Your equation will just be modified to become like this. FB equals to BIL will become BIL sine theta. Okay. Now, if you look at it carefully, what does the sine theta here mean? If you look at it another way, FB is actually going to be B and then L I sine theta. If I look at it another way, can be said as this, right? Because you see, my case is that if I had a current I going through here, this current I can be resolved into two perpendicular directions. I can resolve the current into this direction. This one will be I cos theta, and then it can also be resolved into this direction. This one will be I sine theta. Okay, so now what we'll tell you is this: current perpendicular to field is what causes the magnetic force. Okay, current parallel to field does not cause magnetic force. Okay, it does not cause magnetic force. Okay, so when you have current flowing through a wire, yeah, the current has moving charge, which in turn causes you to have a magnetic force. But specifically, what we need to further highlight to you is that it is actually the charge moving or the current moving perpendicular to the field that causes the magnetic force. All right, you must have the current or charge moving in a certain direction with respect to the field to cause a magnetic force. Okay, specifically, you must have current perpendicular to field. That one is what causes you the magnetic force. If you have a current parallel to the field, it won't cause you any magnetic force. So when you have a current that is flowing at an angle to the field, you actually only consider the current perpendicular to the field. You don't consider the current parallel to the field. So that's why when you want to calculate out the magnetic force, it is BIL sine theta. Okay. Now when your wire is perpendicular to the field, that is where you get maximum force. Because you see, if you want FB to be max, sine theta must be max, right? So the only way sine theta is max is when theta is equals to 90 degrees, because sine theta, the max value of sine theta is 1. This occurs at theta equals to 90 degrees. Okay, so just know that when a wire is perpendicular to field, the force is usually maximum there. Okay, because based on this expression, if you want to have maximum force, sine theta must be maximum. The maximum value of sine theta is 1. This can only occur when theta is 90. When theta is 90, the wire is perpendicular to the field. And then likewise, when the wire is parallel to the field, the force will be 0. Because if you consider this one, if your your FB is to be minimum, sine theta must be minimum. Sine theta is minimum at 0, and this occurs when theta is 0. That means that your wire is parallel to the field then. Okay, so your force is 0, is minimum there. Okay, so just, but I think it's better just to remember this. As long as your wire is perpendicular to the field, it's maximum force. As long as the wire is parallel to the field, it's 0 force. If your wire is somewhere between perpendicular and parallel, your force is somewhere between 0 and maximum. That's all. Okay, that part is fine. Okay, then let's see whether you can do one question from here. 26. Hang on, let me have a look. Yeah, you can have a look at page 26. Okay, you can have a look at page 26. Wait, no, let me just. Okay, have a look at page 26. This one is June 18 P41. This one is June 18 P41, question 9. Okay. Oh yeah, another thing that I should have mentioned to you just now was this. When you're talking about length L, this length L must be the length of wire inside the magnetic field only. Okay, the L here, if you want to use this equation, must be the length of wire inside the magnetic field only. It is not the whole length of the wire. What I meant was basically something like this. you say you wanted to use FB equals to BIL to calculate the magnetic force acting on this wire, the L that you will use is just going to be this one. Okay, your wire, the whole length was this. This one is the whole length of your wire. Okay, this is the whole length of your wire. But when you want to use FB equals to BIL, the L will only refer to the length of the wire inside the field. Okay, length of wire inside the field only, not the whole length of the wire. Okay, just so you are clear on that, right? Okay, have a look at page 26 of your magnetic field chapter. Okay, this one is June 18 P41. Now they tell you you have a rigid copper wire that is held horizontally between the pole pieces of two magnets as shown. The width of each pole piece is 8.5 centimeter. A uniform magnetic flux density B is in the region between the poles and is of value 3.7 millitesla and is 0 outside the region. The angle between the wire and the magnetic field is theta. The current in the wire is in the direction shown. By reference to the side view of figure 9.1, which is basically this one, state and explain the direction of the force acting on the magnets. Here they're asking you to explain the direction of force on the magnet. Okay? They want the force acting on the magnet, not the wire. They want the force on the magnet. So how would you go about in doing this? This one they just want by reference to the side view, which is this one. Okay, and they want the force acting on the magnet. So you need to use Fleming's left hand rule again, where we tell you thumb is magnetic force, index finger is magnetic field, middle finger is current. So you can identify a few things. This one, as I mentioned to you, is going to be the current in the wire. This is the magnetic field the wire is in. This is the magnetic field. This is the magnetic force acting on the wire. So if you apply it to this case here, the direction of your magnetic field is from north to south. So your B is here. The direction of current is from left to right. So your I is here. So if you apply Fleming's left-hand rule, you will easily be able to see that your magnetic force is actually outwards. The magnetic force acting on wire is outwards. So, but the question was the magnetic force acting on the magnet. So, you know that if the force acting on the wire is outwards, the force acting on the magnet must therefore be opposite because of Newton's third law. So the force acting on the magnet is downwards because this is a consequence of Newton's third law. All right, but how would you explain it? You explain it in this manner. Okay, this one is what question 9. Sorry, I need to go to question 9. Yeah, which is this one. So you just say something like this. By Fleming's left-hand rule, the magnetic force on the wire is acting outwards. By Newton's third law, the force on the magnet should be acting downwards. Okay, so that part is right. Right. Now for part B, they tell you the constant current in the wire is 5.1 ampere. For angle theta equals to 90 degrees, calculate the force on the wire. Now, for the part where they tell you angle theta is now 90 degrees, that would have meant that your wire is now perpendicular to the field. Because you see, this is your angle theta is measured like this. If your theta is 90 degrees, that means your wire is perpendicular to the field already. Okay, so this one here, you know that wire is perpendicular to the field. So if your wire is perpendicular to the field, you know you can use F equals to PIL straight. Okay, so your magnetic flux density is 3.7 millitesla or times 10 power minus 3. Your current is 5.1. Your length is the length inside the magnetic field. So the length inside the magnetic field is going to be 8.5. It was basically going to be the same as the length of your magnetic poles. Okay, so it's going to be that value. You get 1.6 times 10 power minus 3 Newton. Okay, so that part is fine. All right. So if nothing else, then we go on to this part. Right. So if you're okay with this, then we go to the next part. Now the next part, they tell you the length, the angle theta is now changed to 60 degrees. It's now at an angle to the field. The length of the wire in the magnetic field itself is already given, where they tell you is 8.5 divided by sine 60 centimeter. Calculate the force on the wire. Now for the case where the wire is at an angle to the field, it will be BIL sine theta, right, as I mentioned to you. So the B is 3.7 millitesla. The current is 5.5 amps. The length is going to be the length inside the magnetic field. It is not going to be 8.5 itself. Okay, because 8.5 itself is actually just going to be this one. Okay, this line. But that is if your wire was straight line. If your wire was perpendicular to the field, it would be correct to say that the length L is 8.5. But when it is at an angle, the length you have to consider is the length that is inside the field itself. It won't be 8.5. But luckily, they've already told you what the value is. It's 8.5 over sine 60. It's referring to this one in the first place. So you just put that one in. But when you put that one in, you need to be careful. They gave you that length in terms of centimeter. So you have to change the centimeter back to meter in the first place. Okay? Then your sine theta, your theta is actually just 60 degrees. You sub that in, you get this answer. Okay? Right? So this is what you have. Then you get the answer is 1.6 times 10 power minus 3 Newton. Okay? It isn't really that different. Yeah, the answer is actually the same as the previous question. Alright? So what's the work with this? Right. So there's another part here. Yeah, you did not have the other part. Never mind. Okay, so this part is fine. Now there's just one last part that I probably should go through with you. Okay, now if say for example you want to find out the magnetic flux density, I will go back to the notes now. If say for example you want to find out the magnetic flux density of the magnetic field that your wire is in, there are certain ways in which you can find out the magnetic flux density of the magnetic field that your wire is in. Okay, one of the ways was basically to use this equation F equals to BIL. You know the length of the wire, you know the current inside the wire, you know the magnetic force on the wire. You can find out the magnetic field strength or magnetic flux density of the magnetic field that the wire is in. Okay, there's another way in which you can also do that. That one is by using something similar to this. All right. What we will tell you is that you need to have a wire that is already bent to a square shape like this. You support the wire on a pivot. Okay. What you do is that you run current through the wire. So you make sure that that wire with the current running is between two different magnets with a magnetic field in between. Okay. So the idea is that if you look at it, this apparatus from the side, it will look like this. Okay, where this one is your pivot. Okay, and this part here is here. So what you want is that you want current to run through your wire in such a way that you have a magnetic force acting downwards. Okay, so what you then do is that this other end here, you want to put some weights onto this end. Okay, you see, if you don't put any weights here and you only have a magnetic force here, your wire will start to tilt downwards. Okay, so what you want to do is that you want to put some small weights here so that you apply a counter moment so that the wire balances. Okay, so if the wire is balanced, for example, if the wire is balanced, what we'll tell you is that the clockwise moments will be equals to anti-clockwise moments. Okay, all right. And if say this one is say distance x1 and say this one is distance x2, this will mean that wx1 is the same as fb x2. Okay. Now, if pivot is exactly in the middle, that would mean that x1 is equals to x2, right? So that would mean this. You will get wx1 equals to fbx1. The x will cancel, so w is equals to fb. Okay. Then after that, this one you can expand the equation. It becomes b I l. From here, you can actually work out what is your value of b. Okay. Right. That's what this thing here is actually trying to tell you. Okay. In essence.